Okay, so now that we have learned a method to approximate some irrational numbers such as square roots of non-perfect squares, and we already know how to find the decimal expansion of rational numbers, we're going to be using some of the skills that we've acquired to compare some of these numbers. We'll be comparing irrational numbers with irrational, and then sometimes an irrational number with a rational number. Okay, so in this lesson, there are 11 exercises, and this is an exploratory challenge. So you have the skills to do these problems. You can use a calculator to check your answer, and you can use a calculator to do some of the rational approximation of the non-perfect squares, but the off limits until your answer would be the using the square root or the cube root button just to crank this out, okay? And also using the division button to crank this out, okay? So use the calculator the least amount you can. You can use it the way we used it in the last lesson, in lesson 11, to do that rational approximation. Otherwise, see what you can do just with your brain and with paper and pencil. And then, so try these. Numbers 10 and 11 get a little trickier. So if you're doing great, you could attempt those. Otherwise, you can come back and look at my solutions to these one by one as you go through as well. So if you have someone to work with, that's great. Otherwise, work on your own and just watch one by one with these problems. So go ahead and pause now and at least try the first one, if not several of these, before coming back to check. Okay, so let's look at this first one. Rodney thinks that the cube root of 64 is greater than 17/4. Sam thinks that 17/4 is greater. Who is right and why? Okay, well, the first thing I want to do is to see what is the decimal approximation, not the decimal, but the decimal representation of 17/4. So I know that 16 is a multiple of 4. So I know I can divide this into 16/4 plus 1/4. So this becomes 4 and 1/4. And I can also write it as 4.25 if I wanted to. Okay, so it's 4 and 1/4. And I know that the cube root of 64 is going to be the number that I multiply by itself, use it as a factor 3 times to get 64. So I know that 64 is 4 times 4 times 4, or 4 cubed. So the cube root of 4 cubed is just 4. So now I can compare these two decimal representations of these numbers, and I can see that the cube root of 64 is less than 17/4. Okay, so who's right? So we would say Sam is correct. Sam is correct. Okay, because 4 and a little bit is greater than 4 and 1/4 is greater than 4. Okay. Okay, next problem. I'll give you a second to pause if you haven't attempted it yourself yet. Okay, so one of these numbers is a rational number, 2.89, just written as a decimal. And the cube root of 27, again, is that number that I use to multiply by itself, use itself as a factor 3 times to get 27. And I know that 3 cubed is equal, whoops, not 3 squared. 3 times 3 times 3 is 27. So the cube root of 3 cubed is 3. Okay, so I'm able to compare these numbers now pretty easily. Since the cube root of 27 is 3, I know that 2.89 is less than the cube root of 27. And so I could write it that way. Okay, next one. All right, so what I'm going to want to do is find rational approximations or equivalents to these two. So I know that 121 is a perfect square, right? So the square root of 121 is 11, because 11 times 11 is 121. The cube root of 125 is the number that I multiply by itself 3 times, and that's going to be 5. 5 times 5 times 5 is equal to 25 times 5, right? Which is equal to 125. So the cube root of 125 is 5. So therefore, the cube root of 125 is less than the square root of 120, the square root of 121, because 5 is less than 11. Okay, let's continue. So 4, which number is smaller, square root of 49 or the cube root of 216? So again, I want to find the equivalence of these. 49 is a perfect square. 7 times 7 is equal 49. So the square root of 49 is 7. The cube root of 216, I'm going to have to think about a little. So if you remember your cube roots, which we don't work on those as much, but 6 times 6 times 6 is equal to 36 times 6, which is 216. Okay, so the cube root of 216 is 6. Now this might take a little bit of guess and check to find some of these. So it's not a problem if you had to guess and check with the cube root of 216. You know, you might guess something like 10. 10 times 10 times 10 is equal to 1,000. So I know, you know, the cube root of 216 has got to be less than that, right? So I could begin checking some numbers. So what do we know then? We know that the cube root of 216 is less than the square root of 49. Which number is greater, the square root of 50 or 319/45? Okay, so this one's getting a little bit trickier, and we are going to need to do some, you know, a little bit of calculating on this one. So let's start with the rational number, 319/45. So this is 319, and I'm just going to use long division. 319 divided by, let's give myself a little more room. 319 divided by 45. Man, so I'm thinking, how many 45s are there in 319? And I know there's at least 6, maybe 7. So I'm going to start with 7. And I know there's at least 6 because there's 6 50s in 319, right? So 7 times 45 is 35 there, 28, and 315. And so I have a remainder of 4. I carry out this decimal. My next digit's going to be 0 because 40, There's no 45s in 40. So this next digit is less than 10. We'll try 8. 8 times 45. Now I know this is either going to come out even at some point or repeat. So I want to do it until I get enough to be able to compare it to my other number. So 7 times, 8 times 45 is, 8 times 5 is 40, 32, 36. Okay, and then I get a 4 again. Or no, I don't get 4, I get 40. I get 40, bring down a 0, so that means these are going to continue to be 8s. This is 360, there's 40 left over, and so I'm going to get another 8. So this fraction, 319 over 45, is equal to a repeating decimal that I'm going to write like this, 7.08 with the 8 repeating. All right, now square root of 50, I know square root of 50 is pretty close to 7, but it is, it's greater than 7. It's a little bit greater than 7, square root of 50. So that doesn't help me yet. I know that, let's put it this way. I know that it's greater than 7 and less than 8. Okay, so that doesn't give me enough information yet to compare it to 319 over 45. Because our number 319 over 45 is also between 7 and 8. And I know that 50 is really close to 7. So I could try 7.1 squared to see what that is. 7.1 squared. Now here's where you could use a calculator. I haven't used a calculator yet on these problems, so hopefully you haven't either. So 7.1 times 7.1 is equal to 50.41. Okay, so what information does that give us? Well, that gives us an interval of tenths, so I know that the square root of 50 is greater than 7, and now that I know that it's less than 7.1, and the reason I know that is because 7.1 squared is 50.01. That was an important result right there, okay? But I don't know about 7.08 repeating. So what if I tried 7.08? 7.08 squared is equal to, it's equal to 50.1264. And let's just for kicks, let's try 7.07 squared. Okay, so it's kind of like a little puzzle. 7.07 is, 49. This is equal to 49.9849. 9849. So now what do I know about the interval of the square root of 50? Well, I've narrowed it down. Let's go back to purple here. I've narrowed it down. I know that the square root of 50 has to be greater than 7.07, and it has to be less than 7.08. Okay, so I know this. That does not look good right there. Myself a little room, 7.07. Okay, so now I have it in this interval. So now I have enough information because I know that 7.088888 is greater than this number. So my square root of 50, so now I know that the square root of 50, and this is my, hopefully you can see this down there, the square root of 50 is less than 319 over 45. Okay, I'm going to pick a different color. I want to show you, I'm wondering if anyone did this. I'm going to do this so it stands out. What if I took 319 over 45 and squared it? So that would equal 319, times 319 over 45. Those two fractions multiplied. I'm going to do that. We're kind of, to be fair, we're kind of trying to do this without using a calculator, but I just want to show you what this would be. 319 times, let's see, 319 times 319. This number is equal to 50.252 and several more decimal places. It's a finite decimal, but there's several decimal places in this answer. So, so this number here, this rational number, what I did was basically I squared both of them, right? Square root of 50 squared is 50. Square root of 319 over 45 squared is 50.252, so it's bigger. So that's just another another confirmation that the square root of 50 is less than 319 over 45. Okay, so that one was a little more involved. Let's look at another one. 5/11ths or 0.4 repeating. So I'm going to just take a quick look at these numbers. 5/11ths, I'm going to use it like a benchmark fraction. 5/11ths is less than 1/2, right? So this number I know is going to be less than 0.5 because 5/10ths is 0.5, right? So 5/11ths is smaller than 5/10ths. And also I can think of if I have 5 of something, if I have 5 out of 11, I know that there's 6 more to make a whole. So I know that I have less than half that way as well. Okay, and 0.4 repeating, that's also less than half because I've got a 4 in the tens place. So no matter how much repeating decimal I have after this, I know that it's less than 0.5. Okay, so I know these numbers are pretty close together. So I've got to do some work on the fraction 5/11ths in order to compare it to 0.4 repeating. So let's do that. So I'm going to take 5/11ths and so I'm going to just do some long division. 5 divided by 11. Okay, I add zeros on the number because they don't change anything, right? So there's a 4 in the first tens place, which doesn't surprise me. I expected it to be less than 5 there. This is 44. I get 60, and so I'm going to go 1 up, so that's 5, 55. So now I have 5. And then, so this digit will be a 4, and that's 44. I get a 6. So we can see this beginning to repeat now. I've got 5, gives me 55, back to the 50. Okay, so this 5/11ths is equal to a repeating decimal It would have to be a repeating decimal, right? Because our denominator's an 11, so there's no 2s and 5s. I mean, it's not just, there's something besides 2s and 5s. And I know it's going to repeat because this is a rational number here. 5/11 is rational. And so, which is bigger? 0.4444 and so on, or 0.4545. So we can tell by looking just right at this decimal place. The 4/10 are the same, but 4/100 is less than 5/100. So I know that 0.4 repeating is less than 5/11. Okay, so in number 7, I'm going to want to compare the decimal representation of these numbers. So I want to write them both as decimals. So I know this one, I could do long division with this one, but because my denominator is 25, I know that if I multiply by 4/4, I'm going to get hundredths in the denominator, which is going to help me write this number as a decimal number. So 4 times 154 is 4 times 150 is 600. 4 times 4 is 16. So this is 616. So 616 hundredths is bigger than 1, right? Because I've got 600, I could think of it this way: 600 hundredths plus 16 hundredths. All right, so I've got 6 and 16 hundredths. You can write the number just like that, reading it like that. 6 and 16 hundredths. Or I could think of this as 616, 616 divided by 10 squared. So I'd be moving the decimal place 2 places when I do that division. All right, so this is 6.16. So now I need to start working on square root of 38. Let's just go ahead and use a different color for that one. Square root of 38. Move it out. I can place square root of 38 as pretty close to 6, but greater than 6, because this is greater than the square root of 36 and less than the next perfect square, which is square root of 49. Okay, so square root of 38 is between 6 and 7. All right, so is this number though. So I need more information. I need to go out to another decimal place. And so I'm going to check decimals in the tens place that are closer to 6 than to 7. So I can check 6.1. And if I check 6.1 squared, I'm going to get, what is it? 6.1 squared is equal to 37 and 21 hundredths. Okay, so I know that 6.1 is too small, so I can try 6.2. 6.2 squared, and again, this is where it's okay to use a calculator. 6.2 times 6.2 is 38.44. Okay, so now what do I know? Now I know that that square root of 38 is between 6.1 and 6.2, because 38 is between 37.21 and 38.44. But my other number is also in that interval between 6.1 and 6.2. So I need to get a little closer. So, you know, this is kind of, if I think of my number line here, I've got 6.1 and 6.2. So I need 6.11, 6.12, 3, 4, 5, 6, 7, 8, 9. Okay, so this one is 6.19. Here, where's 6.16? 1, 2, 3, 4, 5, 6. That one is 6.16. So I still need to know, and I'll make that dot a little bit bigger. Okay, so I need to know if my number is bigger or smaller than that. So I'm just going to try 6.16 squared. And if that is bigger than 38, then I have my answer. And, you know, you could have done that to start with, right? 6.18 times 6.18 is equal to 38.1924. 38.1924. Okay, so 6.12 squared, or 6.16 squared is greater than 38. Oops, sorry. I was double checking that work, and what I actually put in the calculator was that number. 6.18 squared is that. So I know that 6.18 is too big, but now I need to try 6.16 squared, which is what I meant to try. So 6.16 squared, 6.16 is 37.9456. Okay, so now I know that 6.16 squared is less than 38. So therefore, therefore 154 over 25 is less than the square root of 38, which was the two numbers that I was trying to compare. Okay, hopefully you followed all of that. And again, there are many ways to come up with this. I could have, you know, maybe I should have just squared 6.16 to start with. Okay, I could have done that. I would have known that it was smaller than 38. Therefore, 6.16 is going to be less than the square root of 38. Okay, so lots of different ways to think about these. Okay, now square root of 2 and 15 ninths. Okay, so 15 ninths I know is a repeating decimal because of the ninths in the denominator. So if we do the division of 15 not square root, 15 divided by 9, I'm going to get, I should not write it like that, I'm sorry. 15 divided by 9, I'll just write it, that's what you're going to do. You're going to do that long division, but 15 ninths is, I've already done it, so I know it is 1.6 repeating. Okay, and the way I would do this one is to think of 15 ninths as 1 and 6 ninths, which is equal to 1 and 2/3. And 2/3 is one of those repeating decimals that I've memorized. So I know this is 1.6 repeating without having to do the division. Okay, so I know that. But what about square root of 2? I know that the square root of 2 is greater than 1 because 1 squared is 1. And I know that it's less than 2 because 2 squared is 4. Okay, and because 2 is closer to 1 than 4, I know that square root of 2 is closer to 1 than it is to 2. So I can try to narrow it down, and I can find that 1.4 squared is less than square root of 2 squared, which is 2, which is less than 1.5 squared. Let me put those numbers in there. So 1.4 squared, I'm doing on a calculator. And I get 1.96. So 1.96 is what this is. Square root of 2 squared is 2. And 1.5 squared is, you might do this one in your head because 15 times 15 is 225. So 1.5 squared is 2.25. So I've got 2, square root of, 2 is between those. So the square root of 2 is greater than 1.4 and less than 1.5. Since the square root of 2 is less than 1.5, and I can see that 1.5 is less than 1.6 repeating, then I know that the square root of 2 has to be less than 15/9 in answer to that question. And that's because the square root of 2 has to be less than 1.5, and 1.5 is less than 1.6 repeating. Okay? So since 1.6 repeating is 15/9, I can write this statement. All right, let's look at another one. Place the following numbers on the number line in the approximate location. Okay, so if you've had a chance to try this, then you can compare your answers with my solution here. So there's a couple of pretty obvious ones, right? Square root of 25 is the square root of 5 squared, which is 5, equal to 5. And the square root of 36, right? So we can work with those right off the bat. So 6 is the square root of 36, and 5 is the square root of 25. So now we're left with square root of 28, square root of 30, 32, and 35. So we know that they're all going to be in here between 5 and 6 because all of these numbers that we're taking the square root of are between 25 and 36. So we can just start with square root of 28. So it's going to be closer down toward the 25 end of things. So what might be a good thing to do is look at the squares of some of these numbers here. So 5.1 squared is 26.01. And I'm just going to go ahead and do them all because I know that I'm going to need to know these to be able to, and I did these on a calculator. 3 squared is 28.09. So now I know where square root of 28 will lie, it will lie, let me get my circle. It will lie somewhere between 5.1 and 5.2. I mean 5.2 and 5.3. So right in here, because 28 is between here. So we would say that the square root of 28 squared is between 5.2 squared and 5.3 squared. Okay, as the square root of 28 squared is 28. So let's put a dot, and it's closer to 5.3. So I'm going to put my dot up toward that end there, right there. So that would be, yeah, that would be square root of 28 right there. Let's put a green dot for our other two here as well. Okay. So now we're looking for the square root of 30. So let's keep going. 5.4 squared is equal to 29.16. So it's not between 5.3 and 5.4. 5.5 squared is 30 and 25 hundredths. So now I know where the square root of 30 is. It's between 5.4 and 5.5, and it's closer to 5.5. So we'll put it right in there somewhere. Okay, then I'll continue on. 5.6 squared is equal to 31 and 36 hundredths. 5.7 squared is 32 and 49 hundredths. So now we've got our next square root. Square root of 32 would have to be between 5.6 and 5.7. Somewhere right in there. Right there somewhere. Okay, so now we just have the square root of 35 left to do. So I think I'm going to move up closer to, let's move up here, 5.9 squared is equal to 34. Whoops, 34. 34.81. Okay, square root of 35 is going to be really close to that, but a little bit bigger. So I didn't need to do 5.8, 5.9, and a little bit. Get on the line. Okay, so there are our 5 numbers. And you could check the accuracy of this with a calculator, just to make sure you've got them, that we have them placed correctly. I didn't label these though. These are square root 30, square root 32, and square root 35. Okay. All right, now let's move on to the challenge problem number 10. So, which number is larger, the square root of 5 or the cube root of 11? Okay, so we might need to do some hunting around on this one. We know that the square root of 5 is between 2 integers. So the closest square root that's smaller than it is 4. So as square root of 4 is 2. And the next one up is 9, square root of 3. So square root of 5 is greater than 2 and less than 3. And closer to 2, because 5 is closer to 4. So we'll leave it at that for just a minute. And let's think about, let's get the cube root of 11. Let's get a different color for that. Let's talk about the cube root of 11. Okay, so what number could I multiply? If I do 2 times 2 times 2, 2 cubed is equal to 8, and 3 cubed is equal to 27. So the cube root of 11 would have to be greater than 2 and less than 3. Okay, so if we just go to integers, we can't quite compare them yet. Okay, so we're going to have to take it a step further. Let's give ourselves some room. Let's work on the square root of 5, taking that out a little bit bigger. So we think it's closer to 2 than to 3. So let's do 2.2 squared. 2.2 squared would be 4.84. And so that's a little bit too small, so, but not too much too small. So 2.3 squared would be, let's clear this. I'm using a calculator. 2.3 times 2.3 is 5.29. Okay, so we've boxed 5 in here, right? 5 goes in between those two, right in here. So its square root is going to be between 2.2 and 2.3. So let's check 11 cubed. So 11 cubed is going to be way closer to 2 because 2 cubed is 8. Remember, this was 8 and 27. So it's pretty far away from 27. So let's try a number close to 2. So let's try the same 2.2. 2.2 cubed is equal to 10.648. Okay, so that's 2.2 cubed. Okay, 2.2 is a little too small, so I'm pretty sure 2.3 is going to be too big, right? So let's try it. Okay, so we've got 2.3 squared is 5.29, and then times 2.3 again, and now I'm getting 12.167. Okay, so now what we've shown is that the cube root of 11 is in between, because 11 is between 10 and 12. The cube root of 11 is between 2.2 and 2.3. So now we've got it close, and we think it's closer to 2.2. So what if we tried 2.24 cubed, taking it out one more decimal place? Clear, and we got 2.24. Okay, 2.24 is 11.239424. Okay, so 2.24 is too big. We could try 2.23 cubed. See how I'm just going back and forth? I'm adding another place value. We've added hundredths now. 2.23 is still too big. 11.089567. Okay, so I know 2.23 is a little bit big. Let's go back and work on the square root of 5. So we want to go to the next place value. We want to go to hundredths. So we think our number is pretty close to in the middle of this. Let's try 2.25 squared. Now we're back to squared again, right? 2.25. Okay, I messed up. 2.25 times itself is 5.0625. Okay, so that's too big because it's bigger than 5. So I could try 2.24. These numbers are pretty close to each other, right? The square root of 5 and the cube root of 11. 2.24, what's that? Squared. 2.24 is still over 5. Wow, 5.0176. So let's do 2.23. Whoops. 2.23 squared. So I'm taking you through my whole thought process. You might have gotten here a lot quicker. 2.23 times itself is 4.9729. Now, we need to stop and think about what we have. 4.9729. Okay, so what I know now is that the square root of 5, I want you to think about, make sure you know what we know. So pause it if you haven't done that yet. So the square root of 5 is between, 5 is between 4.9 and 5.0176, right? So the square root of 5 is between 2.23 and 2.24. But what I know over here is that the cube root of 11 is going to be less than 2.23 because 2.23 is too big. So we should try, let's try one more. 2, just as a double check, 2.22 cubed, and see what that is. So 2.22 times itself times, no, is 10.941048. So what I know now is I'm going to, we'll write it up here, is that on this side, I know that the cube root of 11 is greater than 2, well, let me write up here, 2.2, and less than, not 2.2, 2.22. Greater than 2.22. Why? Because 2.22 cubed is right here, less than 11. Right? And then the next one that's greater than that, with out to the hundredths place, is 2.23. So cube root 11 is in that interval, whereas the square root of 5, I know is greater than 2.23. Whoops. 2.23. And I know that because 2.23 squared is 4.9729. So that is less than 5. And then the next one, 2.24 is the next number, 1/100th bigger, and 2.24 is more than 5. That's right here, 2.24 squared rather. Okay, so what I know from this is that I can see here that square root of 5 is greater than 2.23 and cube root of 11 is less than 2.23. So therefore, let's get a third color here. Therefore, the cube root of 11 is less than the square root of 5. Okay, well that took a little bit longer than I expected it to, and it was a challenge problem. So it was quite a lot of multiplying that needed to happen and kind of strategizing, but very doable for you. And if you didn't quite understand it, you can call and ask me a question, or you could rewatch that explanation. But basically what we're doing is we're trying numbers, and as we notice that they're too big or too small, we refine our guesses. So that's what's happening there. All right, last problem is number 11, and this might be a bit of a challenge too. So let's read it. A certain chessboard is being designed so that each square has an area of 3 inches squared, or 3 square inches. What is the length of one edge of the board rounded to the 10th place? Okay, so let's think of one of these little squares. Okay, and once again, if you haven't done this yet, you'll want to work on it on your own. So go ahead and pause now if that's the case. Okay, well, each of these is 3 inches. Sorry. The area is 3 inches squared. Okay, so that means if I multiply the side length, we'll call it S, times itself, we get 3, right? So what would the equation for that be? That would be S squared is equal to 3. And so I want to solve for S. So remember, I can take the square root of both sides. That's that property of equality for square roots. So square root of S squared is S, and the square root of 3 is the square root of 3, right? So what we want is the length of one edge of the board rounded to the 10th place. Well, I just found out what that length is, and there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of those on the side of the chessboard. Okay, so I know that the side of this square, let me get rid of this, the side of the board would be 8 times the side of one of the little squares. So it's 8 times the square root of 3. So if I want this rounded to the 10th place, what I'm going to need to do is find the square root of 3 out to the 100th place so that I can round to tenths. Okay, so I'm going to work with square root of 3, which I know is less than 2 because 2 squared is 4, and greater than 1 because 1 squared is 1. So the square root of 3 is going to be closer to 2. So I'm going to try 2, not 2, less than 2. I'm going to try 1.7 squared and find out what that is. 2.89. So 1.7 is too small, and I'm going to guess that 1.8 is probably going to be too big. 18 squared, I'm not sure what that is. 1.8 is 3.24. Okay, so I know it is somewhere in there. We want to go out to hundredths, 3.24. So it's somewhere right in the middle there. So let's try 1.75. 5 hundredths we'll add on. Square that and we'll get 0.625. And so 1.74, looks like we're narrowing it in here using rational approximation. Okay, still too big. 1.73 I'll try. And we'll get 1.73 times itself is finally smaller, 2.9929. So that's only 1/100th off. 1.74. So we're going to use 1.73 for our approximation of the square root of 3. So the side of the board would be 8. We'll call it the width, W. It's either the width or the length, is 8 times the square root of 3, which is equal to, or which is approximately equal to 8 times 1.73, and that's equal to is 13 84/100ths, which rounds to 13, and if we're rounding to the tenths, 13.8 inches for the side length of that checkerboard. I want to talk about another way we could have done this. There's 64 pieces on the board. So we could have said the total area is 64 times 3 inches squared. Which is equal to 192 square inches on the board. So if I had a board and the area was 192, just squared, I could talk about the side length x. Okay, so x squared is equal to 192. So the square root of x squared is equal to the square root of 192. So x is equal to this square root, 192. So I could use rational approximation on this, but instead of going through the steps, I'm going to make a guess. I want to take 13.8 squared and let's see what that is. It is 190.44. Okay, that was our answer, right? We decided to say 13.8 inches. So we're checking it now. So 13.8 squared, sorry, 13.8 squared is 190.44, so that's too small. But let's see if 13.9 squared is closer. $193.21. So 192 is in the middle of those. And we could ask ourselves, is it closer to 13.9, closer to 13.8? Okay, so it's pretty well right in the middle between these two. Maybe about 1.6 away from this one and only 1.2 away from 13.9. So we could say that the side length x is approximately, I mean, we could, with using this method, we're going to round up to 139, and those are inches. Using this method, we're going to leave it at 13.8 inches. Sided board. 13.8 inches. Okay, that was another long one to explain. So here we're at the lesson summary. So this lesson was really nothing new. It was just using the tools that we have, decimal expansion of rational numbers, and we used mostly long division and equivalent fractions for the rational numbers, and we use the decimal expansion of irrational numbers using the method of rational approximation. Okay, so have fun with these problems, and remember that calculators are appropriate to use for multiplying these double-digit and triple-digit numbers, but not for just punching in a square root or a cube root. So see how well you could do on your own. You're going to understand square roots so much better for having done this. Okay, good luck.